Hello everyone, welcome back to chemistry series. In today's session, we'll learn about one of the most fundamental concept in chemical bonding, which is hybridization of orbitals. This topic not only help you understand the bonding and the shape of the molecule, but it also a favorite in exams. So if you're preparing for class 11, 12 and competitive exam, this video is going to be very helpful for you. So let's get started. Hybridization is a concept in chemistry that explains how atom forms bond in molecules. In simple word, it is a mixing of atomic orbital like sp²d² of an atom to form a new orbitals of equal energy is called hybrid orbitals. So we can say that hybridization is a process of mixing atomic orbitals of nearly the same energy in an atom to form a new orbital is called hybrid orbitals. So here you can see one s orbital, which is spherical in shape, mixed with p orbital form sp hybrid orbital. When two orbitals combine in same phase like their waves match, this increases the electron density between two nuclei. Then the bond formed is called bonding molecular orbital. It is like two waves adding up to make a bigger wave. Do you know what is wave? A wave is simply a disturbance that carries energy from one place to another without carrying matter along. In orbitals, electrons behave like waves, as we studied in de Broglie concept. In a wave, there is a few important parts like crest and trough. Crest is the high point of the wave and trough is the low point of the wave. So if I am saying two orbitals combine in same phase, that means their waves match. Crest meets with crest and trough meets with trough. That means constructive overlap. And the bond formed is called bonding molecular orbital. It is like two waves adding up to make a bigger wave. And when I am saying two atomic orbital combine in opposite phase, like crest meet with trough, this cancel out the electron density between the nuclei. That is destructive overlap. And the bond formed is called anti-bonding molecular orbital. It is like two waves cancelling each other out. So in short, constructive overlap means stable bonding. And destructive overlap means anti-bonding, unstable bonding. Next is what are the key feature of hybrid orbitals? Hybrid orbitals are equivalent in energy and shape. They form strong bonds than the original atomic orbitals. And the number of hybrid orbitals formed is equal to the number of orbital mix. That means hybrid orbitals are made by combining atomic orbital of same atom. So the resulting hybrid orbitals formed have equal energy, unlike original orbitals. And each hybrid orbitals has the same shape and size, giving uniform bonding. Hybrid orbitals are oriented in space to minimize repulsion, and the bond formed by hybrid orbitals are stronger and more stable due to better overlap. So number of hybrid orbitals formed is equal to the number of orbital mixed. Here is a comparison table between atomic orbital and hybrid orbitals. Atomic orbitals are present naturally in atom like s, p, d and f. But hybrid orbitals are formed by mixing these atomic orbitals. Atomic orbitals have different energies, but hybrid orbitals have same energy. Atomic orbitals have different shapes, like s orbitals are spherical in shape, p are like dumbbell shape, and d is like clover leaf shape. But all hybrid orbitals are equivalent in shape and size. Atomic orbitals are less directional, but hybrid orbitals are highly directional because they are better overlapped and they form strong bonds. Atomic orbital fixed by atoms configuration, but hybrid orbitals is like number of hybrid orbitals is equal to the number of orbital mix. Atomic orbitals cannot fully explain molecular geometry, but hybrid orbitals accurately explain the bonding and molecular geometry. So we can say that atomic orbitals are the building blocks, but hybrid orbitals are the redesigned tools which nature uses to make its bond stronger. Now let's look at the different type of hybridization. When one s and one p orbital mixes, we get sp hybridization, which gives linear shape, and the orbitals in sp hybridization arrange themselves at 180 degree, like in beryllium chloride, BeCl2. And if 1s and 2p orbitals mix, we get sp2 hybridization, which forming trigonal planar shape as in BF3. And when 1s and 3p orbitals combine, they gives sp3 hybridization, which explain tetrahedral geometry of methane. Similarly, mixing of s, p and d orbitals give rise to sp3d, sp3d2 and sp3d3 type of hybridization, which explain trigonal bipyramidal, octahedral and pentagonal bipyramidal geometry respectively. First is that we will going to discuss is sp hybridization. It is formed by mixing 1s orbital and 1p orbital. It produces two sp hybrid orbitals. These orbitals are equal in energy and shapes. They arrange themselves linearly at 180 degree to minimize repulsion. Like here in this picture, we can see there is one s orbital which is spherical in shape and one p orbital combine to form two hybrid sp orbitals, sp hybrid orbitals. Molecules show a linear geometry, and these hybrid orbitals arrange themselves linearly at 180 degree to minimize the repulsion. All the molecules which show linear geometry, each orbital in these molecules form a strong sigma bond. Like here, I am showing the example of beryllium chloride, BeCl2. In beryllium chloride, beryllium has atomic number 4. So it has electronic configuration 1s2, 2s2, 2p0. Like in the valence shell, it has 2 electrons. So we can say that it has no unpaired electron in its ground state. Because it has no unpaired electron, so it cannot form bond with chlorine. So excitation occur, and in the excited state of beryllium, one electron from 2s shifted to 2p orbital. So in the excited state, electronic configuration is like 1s2, 2s1 and 2p1. P has 3 orbitals and one electron from s orbital jumps to p orbital. Now 2s and 2p orbital hybridized and form sp hybrid orbital. Hybrid orbital. Because here two atomic orbital combine to form sp hybrid orbital, because here one s and one p, that is two atomic orbital combine, it will form two sp hybrid orbitals. And these two sp hybrid orbitals overlap with the orbital of chlorine. Like in case of chlorine has atomic number 17. So its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p5. Here in the valence shell, there are 7 electrons. 2 electron in 3s orbital and 5 in 3p orbital. So here we can see there's one orbital with unpaired electron, and this p orbital overlap with the sp hybrid orbital of beryllium to form sigma bond, and that leads to linear shape. Next is sp2 hybridization. It is formed by mixing 1s and 2p orbital, which produces sp2 hybrid orbitals, which are planar and arranged at 120-degree angles. The remaining p orbital stays unhybridized, and it is usually used in forming bonds, pi bonds, if needed. Like here in this picture, we can see one s orbital and two p orbital, px and py, hybridized to form 3 sp2 hybrid orbital. 3 sp2 hybrid orbital. So 1s and 2p orbital combine to form 3 sp2 hybrid orbitals. They arrange themselves in space at 120 degree, and the shape will be trigonal planar. Each sp2 hybrid orbital form a sigma bond. Like here I am giving an example of BF3, where boron has atomic number 5. So its electronic configuration is 1s2, 2s2, 2p1. It is the ground state, and on excitation, this is 1s, which has 2 electron. This is 2s, which also has 2 electron, and this is p orbitals, which has only one unpaired electron. So on excited state, one 2s electron promoted to 2p orbital. Now the electronic configuration is like 2s, which has one unpaired electron, and there are two unpaired electron in 2p orbital. Now 1 2s and 2p orbitals combine to form sp2 3 sp2 hybrid orbital. Each sp2 hybrid orbital overlap with 2p orbital of fluorine, because fluorine has atomic number 9. So its electronic configuration will be 1s2, 2s2, 2p5. So we can say in p orbital there are one orbital which has unpaired electron, and this p orbital overlap with the 3 sp2 hybrid orbital and form the molecule BF3, which is trigonal planar in shape with the angle 120 degree. Next is sp3 hybridization. It is formed by mixing 1s and 3p orbitals and produces 4 identical sp3 hybrid orbitals. These 4 hybrid orbitals orient themselves in tetrahedral geometry for maximum separation. So here in this picture you can see one s orbital and 3 p orbitals combine to form 4 hybrid orbital of sp3, which are tetrahedral in shape. Like in this picture you can easily understand how 1s and 3p orbital combine to form 4 sp3 hybrid orbital. And these molecule which has sp3 hybridization has tetrahedral geometry with 109.5 degree angle, and these molecules have no leftover orbitals. All the p orbitals are hybridized. To understand the sp3 hybridization, we can take an example of methane. So here in this picture you can see this is 1s2, 2s2, 2p2. It is the ground state of carbon. So in the ground state, there are 2 unpaired electrons in the p orbital of carbon. So it needs 4 unpaired electrons to combine with hydrogen. In excited state, one 2s electron jump to 2p orbital, and then the electron fills in the orbital is like 1s2, 2s1 and 2p3. So here we can see there are 4 unpaired electrons. Here in this state, 1 2s and 3p orbitals combine to form 4 sp3 hybrid orbitals. And these 4 sp3 hybrid orbitals overlap with 4 orbitals of hydrogen to form methane molecule, which is tetrahedral in shape. Ammonia is the another example of sp3 hybridization. In ammonia, one orbital contains a lone pair. Due to lone pair bond pair repulsion, the bond angle reduces to 107 degree and the geometry will be trigonal bipyramidal instead of tetrahedral. And why it happens? We will discuss it in another video of this hybridization series. Next is dsp2 hybridization. It involves mixing of one d orbital, one s orbital and two p orbital and produces 4 dsp2 hybrid orbitals. These orbitals are arranged in square planar geometry. It is found in transition metal elements. So this is the square planar geometry and the bond angles will be 90 degree. It is found in transition metal complexes. Like here I am showing the example of tetracyanonickelate, which is a transition metal element in which nickel has electronic configuration like argon 3d8 4s2. So it has +2 oxidation state, and after losing these 2 electrons, it has electronic configuration like argon 3d8 4s0. Now these 3d orbital rearrange like this, and nickel uses 1d 1 4s and 2 4p orbitals. These combine to form 4 dsp2 hybrid orbitals, and each cyanide donate electron pair into each of dsp2 hybrid orbitals. Like here I am showing each cyanide donates electron pair to each dsp2 hybrid orbitals. That leads to the formation of square planar complexes. We will discuss it later in detail in the coming videos of this series. So this was just the beginning of hybridization series. We have covered the basic in part 1. But how do these rules apply to real molecules? That's exactly what we will see in part 2. So don't forget to watch part 2 for complete understanding. Bye bye.